Hello, this is Mr. Joseph, and in this video I'm going to talk about friction. Now, we've talked about friction before as a force, and it contributes to the overall force that might be on an object. Today we're going to look at the actual parts that contribute to a friction force. So first of all, what is friction? Friction opposes the slipping motion between two objects that are in contact. And for example, in this example that you see on the screen right now, you have a box that is moving with some velocity to the right, and the friction force will oppose that motion. So the friction force is pointing to the left in the opposite direction as the box slips along the surface of the table that it's resting on. Let's look at the factors that affect the force of friction. So there's two factors that affect the force of friction. One is the force between the two surfaces, how hard the two surfaces are pushed together. And this happens to be something called the normal force, which we'll look at in a little bit. Another factor that's involved in the friction force is the characteristics of the material of the two surfaces, how rough they are, how bumpy they might be. The more rough they are, the greater the friction force will be. And this is based on the coefficient of friction, which you can see in this equation at the bottom. It's this little goofy looking symbol, and that's called a mu symbol. It's a Greek letter. And coefficients of friction are on your reference tables, which we're going to look at in a little bit as well. So let's take a look at an example of a box that is stationary. So this is the box that's not moving. All right. And we know that there's a force of gravity pulling down on it. This is actually the Earth's gravitational force. Earth is pulling on any object that is nearby it. So that's this force down here on the bottom. It's pulling down toward the center of the Earth all the time. Now, because of Newton's second law, we know that there must be another force that's pushing in the opposite direction with an equal magnitude, so that the forces in the y direction are zero. And that is something we call that's called the normal force. The normal force is the force that the surface is pushing back up on the box. And we have the box sitting on a horizontal surface, and the box is not accelerating up or down. And so the normal force and the weight force, the gravitational force, are actually equal to each other. That is only the case that the normal force is equal to the gravitational force when you have an object that's on a horizontal surface that is not accelerating up or down. So you can't be on a sloped surface, and you can't be in something like an elevator that might be accelerating upward or downward. Those are the vertical forces, so you can see those labeled as in green here. Now let's say we try to pull on that box and try to move it. Of course, it's not going to move until we reach some maximum force. Okay, in this case, I'm telling you that the force that you pull on it is not great enough to make it move. The box is still stationary. And in response to the pulling is a frictional force. The frictional force must be equal to the applied force if the box is stationary, because again, we add up the forces in the horizontal direction and it's not accelerating. Let's take a look at what I'm talking about here. So here we have a box, and let's put an applied force on it of 50 newtons. Now this object is not moving at all, so that means that the value of the friction force must also be 50 newtons, and you can see right there. And if I push on it some more, let's say with 100 newtons, if the box is not moving, which it's not here, it's again going to remain still, and the forces will be equal. At some point, you will reach a force that causes the object to move. So I happen to know if we put another 50 newtons on it, the box will start to move. And you can see that it's moving. The applied force is 150 newtons. You'll also notice that the friction force drops down to 94. That's because friction, the coefficient of friction, does drop when you are moving as opposed to not moving. And we will look at that a little closer in a second. But for now, let's keep looking at static friction force, which is the friction force that results from an applied force put on the box and the box staying stationary. So what is the maximum possible friction force between the surfaces before it starts to move? So we're going to use this equation to find out what the maximum friction force could be. So in reality, this should say Fs max. The maximum force we could have, the maximum frictional force that could result. Okay, so we're going to use the coefficients of friction. They are found on your reference tables in the front. And we're going to do rubber on concrete. This is a dry concrete surface. This is a 5 kilogram rubber block. We want to see how hard could we pull on this before it starts to move. And that would be where the maximum static friction force is. So we're going to use this coefficient of static friction force. So let's see, what is the normal force going to be? Well, we know what the magnitude of the weight force is. It's going to be 5 kilograms, and we're going to multiply that by 9.81 newtons per kilogram to get 49.05 newtons. We know that the magnitude of the weight force will be equal to the magnitude of the normal force because, again, they are going to cancel each other out because we're adding them up to be 0 because we're not accelerating in the vertical direction at all. So we can just write our normal force as being equivalent to that weight force. Our coefficient of friction is taken straight from the reference tables. It's 0.90, and we're trying to find out what the friction force is, the maximum static friction force could be. So that is, we're just going to multiply these together. All right, and that gives us a value of 44.145 newtons. So I can pull on this box with a force, applied force. So I pull on the box with applied force of 44.145 newtons, and a friction force will result with the same value, static friction. And that's the maximum that I could pull on it before it begins to move. All right, so let's go ahead and pull on that same box with a 45 Newton force. Okay, when we do that, we are going to go into kinetic friction. Kinetic friction is the sliding, when the object is actually moving and sliding. We know that the friction force is going to drop. Okay, and so the friction force now will be, we're going to go ahead and calculate this out. Our coefficient of kinetic friction is 0.68. The normal force is still 49.05 newtons. And so kinetic friction force is going to be 0.68 multiplied by 4905 newtons. And that will give us 33.354 newtons. Okay, so this question asks, how fast will this accelerate based on these forces? It will, we need to add up the forces that are on this object. So we have 45 newtons from the applied force minus 33.354 newtons. And we're using Newton's second law equation, which means the forces added up, like that's F net, will equal to the mass of the object times A. And our object is 5 kilograms. And we're trying to find A. So A will be what? We're going to do this. We're going to solve for this, and I get 2.33 meters per second squared for the acceleration of the object. Now it's interesting to note that this objects, once they start to slide, it doesn't matter how hard you push on them. If I push on them with 200 newtons, the friction force is still 94 newtons here. That doesn't change once the object is moving. Okay. Notice now I have the applied force is less than the friction force, so now we're slowing down. Once we get to a point where the object stops, let's keep it going. Once the object stops, the friction force is going to be equal to the applied force, and you can see it jumps straight to 16 newtons because that's how hard I'm pushing on it. And that's because, again, the normal force the friction force and the applied force must be equal to each other because we're not accelerating, so our net force is 0. See, the net force, the sum of the forces, is 0. And it's 0 until I get to some point where I'm above that maximum static friction force. My forces drop down to 94, the friction force. And again, if we stop, we're going to go back to 19 in this case right there. All right, you got some problems to solve, and then you're going to explore using this exact little applet thing too.